When nations build defenses meant to last for generations, they do more than stack concrete and steel. They build puzzles, layers of reinforcements, buried galleries, and chambers hidden beneath mountains and hills. For decades, the safest way to hide a command center, a weapons store, or a strategic silo was to place it underground, beneath the armor of earth and stone. The logic is simple. What swords and shells could not reach, the earth itself would protect. But where there is a fortress, there will always be an answer. This episode is the story of that answer. How engineers, scientists, and military planners turned physics into a device that could reach beneath feet of reinforced concrete and shattered rock. It is a tale of adaptation, of how the tools of war evolved from sheer explosive mass to focused kinetic energy, delayed fuses, and precision guidance. It's a story of how the United States, over decades, engineered a solution to a problem that had once seemed insoluble. The idea of an earth-penetrating weapon was born in the era when aviation and explosives first matured into decisive instruments of conflict. During the Second World War, planners discovered that even large bombs were often arrested by relatively shallow layers of soil and concrete. The British innovations of the 1940s, the Tallboy and the Grand Slam, were not merely large bombs. They were designed to strike fast, carry momentum into the ground, and detonate below the surface to collapse structures from within. They taught a simple lesson. Penetration, not size, could be decisive. That lesson lingered. Through the Cold War, as superpowers built ever deeper bunkers and hardened silos, the arms race took on a subterranean dimension. The Soviet Union carved command complexes and missile silos beneath mountains. The United States responded with research, not only into more powerful explosives, but into the science of impact. Engineers asked questions that sounded abstract, but mattered practically. How does a hardened steel nose behave when it strikes compacted earth at high speed? How does the shape, density, and velocity of a penetrator determine how deep it will go before breaking apart? When should a weapon explode? On contact, after a delay, or after traveling through meters of material? Those early technical questions generated practical tools. Concepts like the use of dense metals for casings, hardened ogives, the pointed front of a penetrator, and delayed action fuses emerged as core design elements. The purpose was to ensure that the weapon carried its energy past the outer defenses and into internal chambers, where a precisely timed detonation could cause structural collapse rather than merely blow away the surface. Yet the physics alone was not the full story. Penetration requires speed. The faster a mass hits the ground, the deeper its momentum will drive it forward. For aircraft-delivered munitions, that meant creating bombs that could survive high-speed impact without disintegrating, which led to innovations in metallurgy and internal structure. For guided munitions, it demanded reliable fusing and sensors that could survive extreme shocks and then trigger precisely when intended. Each technical advance demanded new testing ranges, new instrumentation, and new safety protocols. These were not overnight breakthroughs. They were decades of steady refinement. The Gulf War of the early 1990s offered a practical turning point. During operations in the Middle East, coalition forces found that many key targets, underground command bunkers, hardened hangars, and deeply buried facilities, could not be reliably neutralized with traditional munitions. The need for a weapon that could strike into the ground, and do so with surgical effect, resurfaced with urgency. In response, engineers turned existing knowledge into operational systems. The GBU-28 emerged as an example of rapid adaptation, a weapon developed under pressure, refined through testing, and then fielded to address a specific operational need. It embodied the principles learned from the past: hardened casing, shaped design, and a delayed fuse, but married them to modern delivery platforms and guidance. Following that, the logic of deep strike matured into more comprehensive programs. Planners envisioned not just a bomb that could pierce a single hardened vault, but systems that could reliably reach and neutralize facilities buried under tens of meters of earth or embedded within mountainous terrain. That aspiration gave rise to what would become known in public reporting as very large penetrators, weapons whose defining attribute is not solely their explosive yield, but their ability to carry kinetic energy through material and then detonate at a controlled depth. Designers refined the variables. Increasing mass helps, but it is not sufficient without structural integrity. The weapon must not deform or break apart on impact. Speed helps, but delivery platforms and standoff requirements limit how fast a conventional gravity drop can be. So engineers turned to advanced materials, high-strength steels, specialized alloys, and manufacturing methods that could yield casings capable of withstanding extraordinary stress. They also improved the internal architecture. Cavities and liners that manage shock, and fuses that count milliseconds with surgical precision. At the same time, guidance systems evolved. No longer satisfied with simply getting a bomb in the general vicinity of a target, modern forces insisted on pinpoint delivery. Global navigation systems, coupled with inertial measurement units and terminal seekers, allowed weapons to arrive within meters of their intended impact point. For a bunker buster, accuracy is more than convenience. It is the difference between piercing the intended structure or striking softer ground and failing to reach the protected chamber. Precision thus became a force multiplier. Yet even this was only part of the strategic picture. Modern warfare demands effects, not merely hits. A single weapon that could penetrate a hardened complex might remove a command node, but adversaries learned to disperse, to create redundancy, and to conceal. The offense had to outpace the defense. That meant integrating sensors, intelligence, and targeting cycles with the weapon itself. It required reconnaissance that mapped subterranean layouts, geophysical surveys to estimate soil compaction, and persistent intelligence to identify when critical assets were in place. In short, technology and information had to move in step. By the early 2000s, with classified and public programs converging in some ways, the United States fielded larger, more capable systems. The GBU-57 Massive Ordnance Penetrator, often discussed in open sources as the MOP, epitomized this class of weapon. Designed to defeat extremely hardened and deeply buried structures, it represented a synthesis of lessons learned over half a century. Immense mass, a reinforced casing able to survive high-speed impact, and a fuse engineered to delay detonation until the penetrator had done its work. The MOP was not only about destructive capacity, it symbolized a change in doctrine. Where earlier planners had relied on area bombardment and massed fires, modern strategists sought the ability to surgically remove critical nodes while limiting broader damage. The presence of such weapons reshaped the calculus of fortified construction. Defense planners could no longer assume that depth and concrete alone guaranteed safety. The result was an ongoing arms race, deeper chambers, more complex internal layouts, and the use of surrounding geology as an additional layer of protection. And yet, for every added meter of rock, someone in a lab measured the extra kinetic energy required to penetrate it. Each improvement in defensive design invited a response in offensive engineering. In the last decade, this duel has taken new forms. Advances in materials science opened the door to casings and liners that perform predictably under enormous stress. Additive manufacturing allowed complex internal geometries that manage shock in novel ways. sensors miniaturized until fuses could integrate multi-sensor packages capable of distinguishing soil profiles and detecting entry into voids. Meanwhile, delivery concepts diversified. Beyond straight-line gravity drops, planners explored standoff delivery, where a munition could be launched from afar and guided to a target, and even concepts that use a rocket-assisted boost to increase impact velocity. At the same time, attention turned to the ethics and strategic utility of such systems. Military professionals emphasized that these weapons are tools of last resort, instruments to be used when no other option reliably achieves the objective with acceptable risk. In doctrine, they underscore restraint and precision. The goal is to disable critical infrastructure while reducing collateral consequences. The debate in professional circles is about proportionality, legality, and the long-term consequences of normalizing certain capabilities. Looking forward, research suggests new horizons rather than a single revolutionary leap. Hypersonic delivery concepts talk of increasing impact energies by delivering a penetrator at far higher speeds, though such systems introduce tremendous technical challenges. Alternatives explore the idea of precursor charges that fracture the ground ahead of a penetrator, making subsequent passage easier. Other efforts combine unmanned reconnaissance with kinetic solutions, refining targeting and minimizing the need for repeated strikes. The broader lesson is one of continuous adaptation. Where once concrete shelters seemed invulnerable, the combination of physics, materials, science, and precise guidance has steadily eroded that security. Yet defenses adapt in turn. For every technical advance in penetration, engineers have experimented with dispersal, redundancy, and concealment. The contest below the surface is, in truth, a mirror of the contest above it. Innovation begets counter-innovation, and the field moves forward in fits and starts. In the end, the bunker buster is less a single weapon than a concept, an engineering answer to the question of how to reach what hides beneath. It is a reminder that warfare is technological conversation. For every method of protection, there is an invention seeking to overcome it. The United States' work on Earth-penetrating munitions tells a story of patient refinement, of laboratories and test ranges, and of the careful marriage between intelligence and engineering. As nations consider what to protect and how deeply to bury their critical capabilities, they must also reckon with the implication. Modern conflict is as much about knowledge and precision as it is about mass and force. A fortress may be deep, but knowledge and engineering can be deeper still. And in that depth, strategy finds both its limits and its possibilities.